Good afternoon. I'm Brian Robinson. I'm going to be giving the NEAP presentation for the molten salt reactors materials, RC1. I'll be acting on behalf of Sue Lessica. She is unfortunately on travel. She looked for a volunteer, so I am participating in this presentation. What I wanted to provide you initially was our molten salt outreach that we're doing with industry. On slide 2, you'll see we have several industries that have either won awards from us or are active in the community for MSRs. TerraPower, Terrestrial Energy, Kairos, Thorcon, Flybe Energy, and Elysium are just a few. In participation with these vendors, we have found materials that give us the ability to be specific in some of our calls, and we'll be going through some of that today. On slide 3, limited ASME nuclear code approved materials for MSRs. Obviously, we have 304H and 316 on the list, alloy 800H, 2 1/4 chrome 1 moly, and a modified 9 chrome 1 moly. With these materials have been extended. These 5 materials have been extended to 500,000 design life, being finalized by the ASME code committees. ASME has all needed data and will complete these reviews in the next 2 to 3 years. Alloy 617 is another material. And lastly, these Class A materials are not optimized for the MSR structural applications due to the extreme environment of high temperatures, corrosive salt, and neutron radiations. Now, while that's true, we do also know that many of these materials, specifically 316, are materials that are being considered in either test reactors or prototypes. We wanted to provide you the base of our program. Obviously, we have a lot of experience with molten salt reactors, although it does go back to 65 to 69 with MSRE. We provided some of that information on this slide. The subsequent slide, next slide, we gave you the molten salt reactor experiment fuel and some information on it. And one of the things I wanted to emphasize during this presentation is many of these slides are providing some background, some general knowledge and information for the applicants to be aware. The MSRE is a liquid fuel reactor, thermal spectrum breeder reactor, about 7.3 megawatts thermal, operated at about 662 outlet temperature, and it had a lithium beryllium fluid fluoride salt. This program was canceled when we chose another reactor. The big thing at the very bottom, new interest in the MSRs, is fast or thermal spectrums, liquid or solid fuels. And we have a diverse market on this: baseload, electrical generation, process heat applications, desalination, water for purifications, and also these reactors can be put in remote locations. Next, there are several slides that we're going to go through that I said before. We're going to generally outline some information for materials relative to the MSRs. And I'll go through these. But again, I'm acting on behalf of Sue. So if you have more specific questions, I'm hoping Sam Sham is on the line. We got a thumbs up from him. So any technical questions will be, if I can't answer them, I'll pass them along to Sam. So the first bullet here, we need these to be designed for compatibility with molten fluoride salts. They need to have a minimum chromium, but sufficient to provide oxidation resistance. They do not brittle on aging. They have limited aluminum, titanium, and carbon contents, minimizing fabrication and corrosive problems. Carbides are stable and qualified in the ASME non-nuclear code section 3 to 700 degrees C. There's several post-operation issues identified on this slide. Devens and Evans demonstrated the temperature-dependent solubility of this chromium fluoride and fluoride salts resulted in removal of chromium from the hottest metal surfaces and deposition of chromium on the coolest surfaces. Additionally, we have this other material, INOR8, suffered irradiation-induced brittlement primarily attributed to helium produced by interactions of thermal neutrons with beryllium, which is an impurity in the alloy. Fission products, tellurium, cause shallow intergranular cracking for INOR8 exposed to the fuel salt. The effects of niobium additions on tellurium cracking of Hastelloyland was determined. The effects of niobium additions on grain boundary cracking after exposure of these two chromium tellurium salts for 250 hours at 700 C is presented. It shows 1 to 2% weight reduction, and niobium provides most improvement. Next slide. This slide was provided to give you material examples by country. As you can see, we gave you basically the composition of each material as I said before, by country. Hastelloy N is one for the United States. I'm not going to go through all of these, but again, I wanted to give a fair presentation for everybody to know what materials that we're looking for across many other types of collaboration. For instance, we have some in the U.S. and we'll later talk about potential outreach with the UK. MSR component dose can range from less than 1 to up to 25 dPa. The big point on this slide is the very last sentence: potential for irradiation damage on MSR materials must be assessed. It's a big thing for us. Assessment of available alloys. We provided the structure of metallic structural materials for MSRs. This is the one of the reference material. We gave you the hyperlink for it, and this assessment is available through the MSR is available through this hyperlink. The recommendation is to develop advanced nickel-based alloys for the use in MSRs. Next, we'll go through NEIP structural material research and the needs, these long-term needs for MSR. So RC1, innovative new nickel alloys for MSR structural applications. Proposals are sought to identify existing or to develop new nickel alloys that can be used for welded construction of structural components of MSR designs that use either solid or liquid fuel. Characteristics of the candidate nickel alloys to be considered include, but are not limited to, high temperature strengths, 400 to 600 Fahrenheit for long-term design life, and up to 800 Fahrenheit for short-term excursions. Salt compatibility, irradiation damage resistance, resistance to fission products and brittlement, weldability, and amenable to fabric scale-up. Long-term microstructure stability in the MSR environment is also needed. Continued on the next slide for RC1. Innovative concepts such as exploiting nanoscale interfaces within the alloy to trap defects in helium and novel applications of high-valued experiments with integral computational materials engineering are highly encouraged. While not specifically a part of this activity, the long-term goal of alloys developed under this effort would be their qualifications for nuclear service under ASME Section 3, Div 5. Hence the long-term stability, fabrication, and potential compatibility for commercialization of candidate alloys are important. While not required, the interaction with MSR designers on their system requirements is highly encouraged, and that's one of the reasons why we put the commercial supplier or vendors at the very front. RC1, innovative new nickel alloys for molten salt reactor structural applications. Collaboration with the Engineering and Physical Science Research Council in the UK are also strongly encouraged as UK funding is available for UK institutions participating as collaborators for the scope of RC1. The federal POC for these projects is Sue Lessica, and the technical POC for this is Sam Sham, and he is currently on the phone. And that's the quick presentation, and I'll table any questions that you may have at this moment.
Okay, well, we are going to get Sam Sham on audio right now.
Yes.
Sam,
Can
are
you
you
hear
there?
me? Yes,
we can hear you.
Okay, good.
Okay, we have Sam and Brian here to answer any questions you have. Please do submit those through the GoToWebinar application. Brian and Sam, here's the first question. Can we propose alloys other than nickel alloys?
The scope of this call is specifically for nickel alloys. We had a call from, we had an award from Fy19 on high entropy alloys. So the scope for Fy19 is on nickel alloys.
Should one single proposal address all the characteristics listed, such as strength, fuel salt compatibility, damage resistance, or can we focus on just one?
I will say the following. Obviously, that for given the award, we would like to get as much as we could from the universities, and obviously that if you propose one aspect of the problem that we will assess in sort of in comparison with the other proposals. So I would say that if you address one specific aspects and all of these aspects like a high temperature strength, irradiation resistance, as well as the corrosion resistance, they have synergistic effects. So therefore that if you just concentrate on one, we will not sort of disqualify the proposal, but we will evaluate that in terms of its merits.
So if I'll expand on that. So some places may not have the capability of doing multiple components. I certainly understand that. But as Sam said, the root of this is to get as many of the qualifications, the variables in one proposal. If they cannot do that, we certainly understand it, but we'll be weighting that proposal against the other ones who probably will be submitting everything in full.
Are you interested in new alloy proposals or only testing the current alloys?
We're interested in both. If one looks at the scope, we are looking at either existing alloys that are not in the nuclear code or developing new nickel alloys.
I think one of the struggles there, Sam, and help me out on this, is that something that's new, the push and financial amount, the time to get them developed is much more lengthy and costly. So I agree we're looking for both, but I would certainly suggest that we want to get more information on the ones that we already have a firm handle on.
Definitely, yes. That if there are existing alloys that will sort of address some of the requirements for these applications, that will be terrific. And if not, then we will be interested to sort of get ideas from the university communities as to what things that they can do to sort of help us to address these various issues under this extreme environment.
How can we use DOE data of experimentally evaluated irradiated alloys?
I don't know what specific alloys. In terms of DOE irradiation program, I am not aware of too many irradiation on structural materials that we have done in the recent past. If there are historical data, probably that if one can identify that, we will definitely want to sort of find out where they are. And for nickel alloys, I don't know how much that we have irradiated in the DOE program in the past. So it's a matter of if the data are available, definitely that we will explore the possibilities to the university participants.
For RC1, is it required to discuss how nanostructured nickel alloy fabrication would be scaled up from the lab scale to the industrial scale?
We stated that in the scope, it will be very good for us to have an idea that whatever either existing materials or new materials that it can be scaled up in some fashion. I don't know what exactly sort of the new alloys that the university participants will propose, but basically, as stated in the scopes, that ultimately, all these materials will be used in a structural application. So therefore, that no matter how great is the properties, that if we cannot sort of be able to construct structural components out of that. So I would say that if some indications of fabrication scale up, and that will be very helpful in terms of how the proposal is assessed by the technical reviewers, etc. So we don't want to have some materials that at least that at this state that we have some difficulty in sort of making sort of practical structural components.
What kind/scales of computational material studies are encouraged in coordination with experimental studies?
Well, I think that this is a very interesting question. I will sort of leave that to the universities and all the ingenuities that they will come up with. I think that definitely integrated computational materials engineering is a very important tools that has shown sort of being able to either cut down sort of materials development time, as well as helping to target high-value experiments. And so I would say that go for it. We love to hear any ideas from the university participants.
So I guess my question, I don't know if I heard it correctly. Are they asking what type of computational methods, or can they use computational methods?
My understanding is what kind
Right.
or
So,
scale.
right. So I think to Sam's point is we certainly would we encourage them to submit computational methods, but I think Sam, the question was asking more specifically to what type of models and computational methods were going to be used.
I understand, and I can be honest. I don't know what type. If I know, I will do it already. So I'm sort of trying to get the university communities in terms of using the ICME to integrate with any proposed experimentations or do it on its own to help them to sort of either demonstrate or refine some of these the mechanisms in terms of from the materials perspective to sort of address some of those extreme environment.
What is your priority? New theories and design methodologies or actual chemistry and experimentally confirmed new alloys?
Well, well, our ultimate goal is to have a usable alloys. So it depends. Well, I understand that it's a 3-year program, and also that this is a sort of a mission supporter program. So definitely we would like to see that whatever that is proposed that will be able to have some indication or demonstrate whatever materials that is going to be developed at the end of the 3-year program that will have those attributes that we outline in the scope. It's not very satisfying, but like I said, that this is a very exciting opportunity for me because that we really would like to have the university communities to sort of help us to address these very difficult problems, and we don't have all the answers. And whatever that we can do to promote sort of the collective thought process from the universities to help us to address this difficult materials problem. This is really the objective of this call.
Right. So I would add that either of those are sufficient. But to go back to the base point is that our role here is to utilizing a commercial product and support them and their development needs. So we are in a much more of a supportive role, and either of those that can help us perform that much more expeditiously would be what we would support.
Are you interested in alloy modification around the currently selected Hastelloy or other commercial alloys?
I would go back.
Definitely, I think well, like I have stated and also sort of spell out in the scope is that we know what are the problems, right? The high temperature strength, corrosions, issues with the salt, some of the sort of irradiation induced types of problems. So anything that the university of participants can do to address those, whether it be if there's a existing alloy that we don't know of that can address these issues, it will be great. If there are some modifications to some existing chemical compositions of nickel alloys that can address these issues, it will be great. Or that if you say that, well, the existing alloys or the modification of those won't work, I have a sort of new alloys that will do X, Y, and Z that will address these these three issues. That will also be great. So we don't have really if I can have a structural materials that can address this three very well-known issues for MSR applications, it'll be great. Whether it's existing materials, modifying existing materials, or new materials.
So
Either way, it'll be great.
Right. I was going to add the same thing. It's both. I mean, it's hard for us right now because we're living on a lot of information that's from the MSRE that was 40, 50 years ago. And we're trying to support a lot of commercialization, but they're based on many of the fundamental materials that we already showed everyone. So to sit back and be able to say, well, we're going to take this path or that path, we really don't have a good understanding of it right now. And that's why we're using these NIPs to be able to bridge that and provide that information to us.
Will surface modification of the alloys fall within the scope?
Surface modification. If the surface modification can address the issues that we have outlined, I think that the answer is sort of conditionally yes. But the surface modification is modifying the surface. So, for example, irradiation will get through the material. So this is some of the things that I don't know whether or not that it will address the issues that we have laid out. But if it can, then definitely we're interested. But one has to sort of make the case in the proposals that it does address all this sort of extreme environment conditions.
The last question is one that I'll answer. The participant is asking, how can we initiate and proceed interactions or joint projects with UK universities? And I will remind everyone from yesterday's presentation that we currently don't have more information on the ESPRC UK collaborations. In the past, based on that experience, we do know that the UK typically releases a request for applications or the equivalent of an FOA here in the United States for their researchers. But I would encourage you, for the scopes that are applicable, to make the contacts that you do have in the UK if you have a concept or an idea that you think would work for one of those joint proposals. So those are all the questions we have. Thanks, Brian. Thanks, Sam, for being on the line and answering the questions. We will return in about 5 minutes for our final presentation of the day on cybersecurity. So please join us in about 5 minutes. Thank you.